Good afternoon, everyone. So today is lecture number 12 of this heat treatment class, and these are the today's menu we'll discuss. That is a problem at high temperature and the solutions. So that means what will happen to the precipitation strengthened material at high temperature, or what will happen to the strength of the material at high temperature, and what is the solution to that. And second, we'll discuss classification of heat treatment, and finally we'll look at the plot, which is temperature versus time basically. There is a temperature versus composition, actually temperature versus composition, and we'll see the predetermined temperature and soaking time for different type of steels. And that is for eutectoid steels and hypoeutectoid and hypereutectoid steels. For different heat treatment, what is the soaking time and what is the soaking temperature and what is the soaking temperature and predetermined temperature. So you can see, okay. So I think this part is clear to everybody. This is a very good image showing temperature versus time for precipitation strengthening, right? And now the question is, what happens to the precipitate at very high temperature, right? So you understand, when the temperature is very high, so diffusivity is high, right? The rate of diffusion is faster at very high temperature. So what will happen? It will result in the coarsening of the precipitate. So the precipitate become coarsen up, right? Now, what is the mechanism of particle or precipitate coarsening? So what kind of mechanism is playing over there, due to which the precipitate become bigger in size, or the particles, that is the precipitate, become bigger or coarser? So the mechanism is Ostwald ripening. Ostwald ripening is a very interesting phenomenon. It is completely similar to, if you have seen that, suppose you take a bucket of water and you add some detergent and you try to agitate this water, right? So what will happen? The bubbles will start forming, and you'll see after some times, if you carefully look at the bubble formation, the small bubbles will get disappear and the bigger bubbles will become more bigger and bigger with time, right? You'll see that. The same thing happens to this. So that means what will happen basically, bigger precipitate will grows more bigger at the expense of small precipitate. So that means the smaller precipitate will get disappear with the time, but the bigger precipitate become more bigger due to this high temperature. This means the small precipitate become more smaller and get disappear, and bigger becomes more bigger, right? So finally, at the end, you will having bigger precipitate in the materials. There will be no small precipitate available. So what is the consequence of this? For the same volume fraction of the precipitate, the space between the precipitate become more, and size of the precipitate become bigger. So what will happen if the spacing between the precipitate will be more? Obviously, dislocation will easily go and easily pass away through the precipitates. So the strengthening will be reduced, right? And obstacles before the dislocation will be minimized, because we will having bigger precipitate. Volume fraction is same, but we have bigger precipitate. So obviously, less number of precipitate will be available, right? So this is the consequence at high temperature. So what is the final conclusion? The final conclusion is what? If we have a precipitation strengthening material, that precipitation strengthening material will, in that material, the precipitate become coarser with the time, with the temperature, right? So there is a boundary. That means precipitation strengthened materials should not be used at a very high temperature. It should be used at a high temperature, but the temperature should not be very high, where the precipitate will get soluble and the coarsening of the precipitate will take place. So this happens actually how? Two mechanisms is happening here. Precipitation and dissolution will be there, and reprecipitation will be there, right? That means the small precipitates will get soluble in the matrix first. Then what happens? Then the solute will reprecipitate on the bigger precipitate. So it will grow into bigger and bigger size. Okay, let me show you some videos if I have. Yes, I have some videos.
Sir, Ipsita Misa is requesting to join.
Sure, yes. Okay, look at this video. This video is showing you ostwald ripening. Just look at this one. You can see smaller and bigger precipitate kind of things. And you can see that bigger precipitate will grow in more bigger, but smaller precipitate will disappear with time. Just look at this video. Or you can see that bigger precipitate is engulfing or consuming the small precipitates. Now just look at this one. You can see more number of bigger precipitates are there, kind of thing. You can imagine this black one is just a matrix and these are the precipitates. You can see the small precipitates will slowly disappear and bigger precipitate become more bigger with time. Okay, fine. Now, alloy design parameter for very high temperature application. So the question is now, then how to design an alloy for a very high temperature applications? So this is the concept behind that. dr by dt, that is equal to d gamma xc divided by r square. Right? So here dr by dt is nothing but the rate of particle coarsening. So rate of particle coarsening is depend upon d. It is directly proportional to d, directly proportional to gamma, directly proportional to xc, but it is inversely proportional to r square. What are these things? Diffusivity, interfacial energy, equilibrium solubility, and average particle size. That means the rate of particle coarsening will be more if diffusivity will be more, which basically happens at a very high temperature, and it depends upon the materials, right? Second, if the interfacial energy will be more, particle coarsening will be more. If equilibrium solubility in the matrix will be more, then particle coarsening will be more. But it is inversely proportional to the size of the part, average size of the particle. If the particle size is very small, coarsening will be more. If the particle size is bigger, then coarsening rate will be less, right? So this is the thing. So this equation you have to remember, right?
But sir, it is R square or R2?
R square, R square to the power 2.
Okay, sir.
Right. So now, okay, just look at this one. This is the hardness versus aging time. This is the hardness versus aging time. So you can see that with increasing in the aging time, you can see the particle is become. Suppose I am talking about this plot, first plot. You can see the hardness value is increasing with the aging time. It reaches to a maximum value that is called peak value. Then again with aging time, it is decreasing. The hardness is decreasing. Similarly, you can take any of them. The trend is same. With aging time, the hardness is increasing. It reaches to a maximum value, that is the peak value of the hardness. Again, the material hardness is decreasing with the aging time. But what are these three lines? These three plots, basically the first plot is for high temperature aging, and this one, last one is for low temperature aging. So you understand, if you maintain a high temperature during aging, what will happen? The rate of increasing in the strength is more, right? But if you maintain a very low temperature during aging, you can see that this one, You can able to see that what we can get a maximum hardness if we keep a low temperature, but time requirement is more. At this much of time, you will get a maximum hardness or maximum strength in the material if you keep a low temperature. But if you keep a high temperature during aging, you will reach a maximum value quickly, but the strength or hardness will be not so high. Right? So basically, we try to keep a optimum aging time and optimum aging temperature to get a maximum hardness or to get a maximum strength in a precipitation strengthening material. Right? And this is a very good plot. You can see this is the temperature versus composition plot. And this part is of, can anybody tell me which part is this? Or which alloy system, basically? In the previous lecture, we have seen single phase alloy, two phase alloy.
The two-phase.
FMCB, two-phase alloy.
Yes, two phase alloy. Very good. And this is one of the part only. I'm not showing the whole part. And you understand, this is the solver's line. So this is the single phase, and this is the two phase reason. Right? So you understand. Can anybody figure it out what is happening here and what is happening here and what is happening here? What is happening here?
Solubility increases.
Yes, solubility is increasing. Yes, very good. Solubility is increasing with increasing in the temperature. Or you can say extent of supersaturation is maximum at the room temperature. But if you increase the temperature, the extent of supersaturation is decreasing. Extent of supersaturation is decreasing. Extent of supersaturation decreasing. This point resembles the alloy composition which you have chosen. From here to here is the extent of supersaturation, right? So extent of supersaturation is decreasing with increasing in the temperature. So that's why the volume fraction of the precipitate decreases. This is the reason why the volume fraction of the precipitate decreases with increasing in the temperature. And look at, this is alloy A, this is alloy B. So can anybody tell me, in between alloy A and alloy B, in which case the particle become more coarsen or the precipitate become more coarsen? You have to compare this equation, correlate this equation with this image. So this is alloy A phase diagram, this is alloy B phase diagram. So in between alloy and alloy B, in which case the particle become more coarsen. Again, this is solver's line. This is solver's line. This is the temperature axis. This is the composition axis. So this is single phase region. This is single phase region. This is two phase region. This is two phase region. Just look at this equation.
Sir, in alloy B.
Yes, in alloy B, the particle will become more coarsen. Why?
dr by dt directly proportional to equilibrium solubility.
Yes,
Sir.
very good. It is directly proportional to Xc, right? That is the answer. So equilibrium solubility is increasing in which case, and increasing in faster rate in which case?
B case, in alloy B.
B case, yes. How? Because this is the solubility, you understand. From here to here, you can see with increasing in the temperature, solubility is increasing. So particle is becoming more soluble in the matrix with increasing the temperature. But here, equilibrium solubility is very less. Very less. Right? Because you understand, this single phase is your matrix, this single phase is your matrix, and this is the two phase region. Beta will precipitate. Here beta will precipitate. Anyways, very good. So what is the solution to very high temperature application? So dispersion strengthening is the solution. Instead of precipitation strengthening, we can go for dispersion strengthening. Or sometimes we can go for both. Precipitation strengthening will be there and dispersion strengthening will be there. So in dispersion strengthening, you understand why you can use, listen it carefully, you can use two type of strengthening at very high temperature, or you can go for only dispersion strengthening. But if only precipitation strengthening will be there, the precipitate will get soluble and it will grow with time, right? So Xc is important. You can see for dispersion strengthening, Xc, equilibrium solubility is 0. That means the dispersed solid will not get soluble in the matrix with increasing in the temperature. They're stable at that temperature, right? Because dr by dt is directly proportional to Xc. Precipitate Xc is decreases sorry, increases with increasing in the temperature. But Xe will be not affected by your dispersion strengthening because Xe is 0. So if Xe is 0, you understand dr by dt is also 0. Yes or no?
Yes, sir.
Xe will be 0 means dr by dt will be 0. There will be no particle coarsening, right? So that's why dispersoid are very good at high temperature. Dispersoid, if you remember, basically we can use alumina particles, we can use yttria particles, we can use thoria particles. These are oxides basically. So oxides basically do not grow with increasing in the temperature. So there are certain steels called ODS steel, oxide dispersion strengthening steels. They are find application in turbine blades, in aircrafts, turbine blades in the power plants, nuclear reactors where temperature is very, very high. Basically, nuclear reactors have a very high temperature. So there we are using ODS steel basically. Turbine blades, we can use this precipitation strengthening material. In nickel-based superalloys, we also use this kind of strengthening mechanism. Precipitation strengthening plus dispersion strengthening. Right? So this is a solution. Okay, finally, heat treatment classification. So now this is our main topic, which is heat treatment. So heat treatment can be classified into bulk heat treatment. It can be classified into surface heat treatment. So bulk heat treatment means the bulk of the material will be taken to the predetermined temperature. Entire bulk will be in the transformation temperature range, right? That means from the surface to the center and center to the surface, everything will be in the transformation temperature range during heat treatment. But surface heat treatment means only the surface will be there in the transformation temperature. The bulk will be not there in the transformation temperature. Or you can say the core part will be not there in the transformation temperature, only the surface part will be there in the transformation temperature, right? So that means we can heat the surface like 1 mm or 2 mm of the surface to the transformation temperature, but the bulk will be not get heated up over there, right? And surface heat treatment can be classified into thermal, thermochemical, and thermal. Thermal means you understand only heat is applied to the surface of the material. That means surface will get heated up to the temperature which we require, right? But here what happens? Thermochemicals means heating will be there on the surface and we are adding some chemicals to the surface, right? For example, we can add carbon, we can add nitrogen, we can add carbon and nitrogen to the surface during heating onto the surface. But here in thermal, only heat will be there, no chemicals will be there. So these are the examples. So bulk heat treatments, annealing, normalizing, hardening, tempering, mar tempering, os tempering. These are different class of heat treatment, bulk heat treatment. And in case of surface, thermal surface heat treatment, we have flame hardening, induction hardening, laser hardening, electrobeam hardening. And in case of thermochemical, we have carburizing, where we are using carbon atmosphere. Nitriding, we are using nitrogen atmosphere. Carbonitriding, we are using carbon and nitrogen atmosphere both. And temperature is also very high. And here again, annealing heat treatment can be classified into full annealing, recrystallization annealing, stress relieving annealing, and spheroidizing annealing. So all these annealing have different purpose. So different thing will be there. We'll discuss that in coming lecture. And already I have written over what is bulk heat treatment, right? Now, as we have discussed many heat treatments, so what is the predetermined temperature and what is the soaking temperature? So you can see this is the 0.8 weight percentage of carbon. This is the temperature axis, this is the weight percentage of carbon axis in steel. So 0.8 weight percentage of carbon steel means this is the point here, right? So above this, okay, above this point, what is the phase? Above this point, what is the phase?
Austenite.
Austenite phase, very good. And this is the ferrite, and this is ferrite plus austenite. And this one?
Austenite
What is
plus
this phase?
cemented.
Austenite plus cemented, very good. So that means if we have a eutectoid steel, right? This is the transformation temperature. Above this, austenite will be there. Anyways, you understand, you remember all these things. Anyways, and this is the hypoeutectoid steel, and this is the hypereutectoid steel. So you can see what is the annealing temperature and normalizing temperature. You can see it is above A3. That means if we have a hypoeutectoid steel, our annealing, if I am doing annealing heat treatment and if I am doing normalizing heat treatment, then I have to go above A3 or AE3, right? But for if I have a hypereutectoid steel, then condition will be different. I will tell that in the coming lecture. But if you are doing periodizing heat treatment, if you are doing recrystallization annealing, if you are doing stress relieving annealing or periodizing annealing, then the temperature should be below A1. You have to remember. That means we do not have to heat the steel above this. So now, can anybody tell me, in periodizing annealing, in recrystallization annealing, in stress relieving annealing, phase transformation will be there or not? See, after predetermined temperature, soaking temperature, finally is the cooling temperature. You have to cool the sample. If you remember the heat treatment cycle, heating cycle, holding cycle, and cooling cycle. So after cooling, you people will get any transformation here? In this case? Periodizing annealing, recrystallization annealing, and stress relieving annealing?
No, sir.
You will get yes or no?
No, sir.
No, very good. Why you will not get any kind of transformation?
Because the same phase is there.
Same phases is there. Can you
Sir,
explain
the
it on the basis of temperature?
phase is changing after T1, above T1.
T1, nothing is T1 here.
So that eutectoid point temperature.
That is T1 or that is A1?
A1, sir.
Yes, above A1, only A1 or any other thing are there? Any other thing?
A1, A3,
Yes, A1, A3 and
ACM, but we don't go above ACM.
we don't go above ACM, but sometimes we go above ACM. If you are doing normalizing for an hypereutectoid steel, we go above ACM. But if I am doing annealing, then I have to go to this temperature in between ACM and A1 for hypereutectoid steel. You have to remember that. That is very interesting. Why? I will tell you in the coming lecture. So you understand, in periodizing annealing, recrystallization annealing, and stress relieving annealing, there will be no phase transformation, right? Because the temperature is below A1 temperature. That is the answer. But if I'm doing annealing, this is called actually full annealing and normalizing. If you are doing annealing and normalizing, then you have to go above this temperature, and upon cooling, you will get phase transformation. The austenite will transform into perlite or something else, depending on the situation. Basically, to perlite. So this is very important for your exam point of view, and for your interview point of view. This is very important. And you have to remember, if I have a hypereutectoid steel, for normalizing, I have to go above SCM. But if I have a hypereutectoid steel and I want to do full annealing, I do not have to go above SCM. I have to remain in this temperature range. I have to go above A1 but below SCM, or in between, you can say. Why this is why I will tell you in the coming class. Okay, so I will end this topic here. If you have any doubt, you can ask me right here. If you have any doubt, you can ask me right here.